Hello, everybody. Today we're going to discuss the calculus of food technology with your host, me, Audrey Netania Mezani Tikoalu, soon to be Sarjana Teknologi Pertanian. #manifest. Of course, we ask, why calculus? Well, calculus is the mathematical language used for understanding change applied in science and engineering in order to solve problems that algebra may not. There are two main branches of calculus, which are differential calculus, which studies the rate of change, and integral calculus, which studies accumulated quantities. Who invented that? Well, we know this guy. This is Sir Isaac Newton. His calculus is called method of fluxions and fluents. He discovered the concept of limits and developed it, all while working on problems in physics and motion. But do you know this guy? This is Gottfried Leibniz. He was actually the first to publish calculus. His systematic notation is now the standard dy dx for derivative and f of x dx for integral. Leibniz's method is easier to use and still used up until today. In food technology, calculus is used to predict food properties, to model, analyze, optimize food processes, help engineers design safer and efficient production systems, all while increasing product quality, consistency, and reducing waste. Alright, that's one off the checklist. Next is real-life applications. Food tech applications? Well, yes, thermal processing such as pasteurization, sterilization, cooling, freezing, thawing, drying, reaction kinetics, fermentation, microbial growth, spoilage and shelf life prediction, fluid dynamics, osmosis, diffusion, water activity, texture, and rheology, all basically almost everything includes calculus. Let's check out some examples, shall we? Or rather just one. Suppose you are a food engineer modeling a canned tuna production system. You're required to figure out the cooling time needed after retorting process. On your left here is a retort sterilization machine, in case you didn't know. I'm gonna give you time to read the question by yourself. 3, 2, 1. Alright, now let's make it easier. We're gonna find the cooling time after retorting process using Newton's calculus. This is Newton's cooling law, which is the rate of change of temperature over time equals the constant of cooling minus delta T, which is initial temperature minus ambient temperature. But in this case, we're going to use TW because we're using water to cool down our canned tuna. Let us derivate.
Okay, let us derivate Newton's law of cooling. First, we're going to separate variables. And then we're going to integrate each left-hand side and right-hand side of the equation. And then we're going to turn it into a natural logarithmic shape. And we're going to exponentiate. All right. That gives us e to the power of minus kt, which gives us the exponential equation of cooling.
After derivating, we get the exponential cooling law. Let's use that to find our cooling constant. Insert our equation, insert the numbers we have, take natural logarithmic form, and we get k equals negative 1 over 6 ln 55 over 106. Using our calculator, we get k equals 0.10935 per minute. Now that we have our cooling constant, let's find our cooling time. Use our exponential equation again with the numbers on the red box above the graph as you see on your right side, and we're going to use natural logarithmic form to solve t equals 1.667. I'm sorry, I had to do that. 70682 over k. Insert our k value, and we have 15.25. Thus, the time needed to cool canned tuna to 35 degrees Celsius is 15.25 minutes, or 15 minutes and 15 seconds. As a summary, calculus isn't just abstract mathematics. Calculus supports food sustainability and innovation and makes it possible to transform intuition into measurable process with pinpoint precision. I think that's all from me today. Thank you for listening. Have a great day and God bless.